Hi everyone, I'm Matthew Ryals and welcome back to the channel. I'm finally back with a new episode of my Patch Programmability series. Today's video is all about patching up your own random gate signals. I'm going to try to patch up from scratch 3 common gate signals and processors. The first one is going to be a probability gate skipper, or a random gate subtractor. This is a kind of module that allows you to control the probability that a gate will pass from its input to its output. Noise engineering makes some modules that have this functionality. Then I'll patch up a random gate source. This will just produce random unsteady gates, similar to a burst output that you might find on a module like Make Noise's Wogglebug. Then I'm going to try to patch up a Bernoulli gate, similar to the module Branches by Mutable Instruments. Branches takes an incoming gate signal and chooses between 2 different outputs based on a probability control. Let's get started. So for these patches, I'm going to use these 2 generate 3s, which are oscillators. One of them is tuned a little higher and one a little lower. In our patches today, there are going to be a few different modules that are really going to help us out. And by modules, I don't mean necessarily specific brands, I just mean functions. So one of those is a noise source and a comparator. And I'll reveal some more of what we need as we move along. So in all of the patches today, noise and a comparator are going to be important. So let's actually just see what we can do with those 2 modules and our sound source. So let's just actually listen to this noise source for a second. Just to acknowledge, yes, this is a noise module and it is working. Now what I want to do is run this noise into the comparator. So this is a window comparator, and what I like about window comparators is that you get to design a window, which is a range, and if the input is in that window or range, you get a high gate on the output. If the input signal is not within that range you've chosen, then you do not get a gate output. Now compare to actually has a not output as well. So that is high when the signal is not in the range you've designed. And so you can control the size of the window. You can control, and you can shift it up or down in range. So let's see what kind of results we get here. We'll take this output and trigger this contour 1, which is an envelope generator. And we'll take the output of contour 1 and we'll run it into our VCA. I actually really like that sound. It's kind of like radio static or something. But let me see if I can fine tune the parameters so we get some random gates. So to get these random gates, I've had to set the size quite low, because if I open it too much, there will be so many gates firing, we'll actually eventually get audio rate gates. And that noise will start to become more apparent. So let's see what happens when we move shift around. So as long as size stays very, very low, shift is okay, but all we have to do is open it up a tiny, tiny bit, and we get too many gates firing, and we enter audio rate again. So as we have learned, this patch works. It produces random gates, but we don't have much range on these knobs, and it's not synchronized to anything, and we can't really even speed it up much at all. So there's not much control here. It's difficult to fine tune, but it definitely works and could be usable. It could work in a pinch. But anyway, let's move on to our first patch. We're going to try to improve on some of these weaknesses here. Okay, so we know we want to improve the results we were just getting, but I also want to steer us in the direction of creating that probability gate skipper or random gate subtractor. One of the additional key ingredients is going to be a sample and hold. And I'm going to use the sport modulator for that. So I'll run the noise source into the sample and hold. And like all sample and holds, we're going to need a clock, and I'm going to use the sport mod top channel, which I already have cycling as that clock. I'll take the end output and go into the sample and hold clock input. And now we're already getting the noise sampled at this clock rate, as we can see on this light. Now I'll go ahead and run that sample and hold output into the comparator. And now I'll begin fine-tuning the controls. So now we are getting random gates, which is nice. So since we're trying to subtract gates, it's going to be helpful to listen to this original clock, which is why I have this other generate 3 ready to go. Now we can actually hear that some of the gates are skipped. I'm going to play around with the size and shift parameters on the comparator a bit. So since shift is controls where we are shifting that window, I have found that it works best if shift is pretty high, so that you're just getting the top end of the sampled noise. So only the highest voltages from the sample and hold are going to pass through the comparator. Of course, this all depends on the size as well. And size is going to be kind of like our probability control. If I have it turned up to maximum, all the gates should pass, as we can see on this white light. And if I turn it down lower, we're going to subtract. And we'll subtract all of the gates if the size parameter is fully counterclockwise. So you might have noticed with size fully open, we don't hear all of the gates passing, and that's because the comparator window is just open, and it only sends a gate when it opens. And the gate is high as it stays open. Now we're hearing a few pass, and that might be due to shift size, or it might be some limitations on how sample and holds do take a tiny fraction of time to sample a new voltage. I've tried many sample and holds, and even though they're extremely fast at sampling a voltage, they're not instant. They're almost instant. And this may be reacting to some really, really fast changes in voltage every time it samples. I'm not sure. But we want every clock signal to be passing right now because we have turned the probability control to maximum. So I'm going to use AND logic so that when the original clock is high and the window is open, we'll get a high gate. And in this case, in this specific comparator's case, I'm going to need to run it through the second comparator. I could also just use an external AND. So here's a copy of the clock right here on the stackable cable. And I just want to see this clock going up and down. So I think this is doing the job. And now let's see if this works. Instead of taking from this output, now I'll take from the AND. And now let's see if our probability control is working properly. Okay, now this should take away some of those gates. I think it can take a little while to fine-tune this. So there's maximum. We're getting a fair amount of gates skipped. Now it kind of feels like 50-50 roughly in here, which would make sense that this doesn't align perfectly like a module you would buy for this purpose, because, you know, all the parameters in that module are going to be fine-tuned for this one purpose. Here we're designing it ourselves. That also probably means the minimum setting doesn't have to be all the way turned down. Okay, but this is working. We have probability control. I mean, it's pretty great. Let's try some different clock rates. Nice. It works really well. All right, let's move on to the next patch. So now let's move on to our second patch, which is just going to be free random gates. I would like it to behave somewhat like a burst output on a random module, kind of like make noises woggle bug. And this will be similar to what we were doing earlier with just the noise source and comparator prior to bringing in the sample and hold. But we're going to have more control now. So the reason why I didn't start with this patch is because it's actually easier to build off the probability gate skipper. So all we need to do is add a little feedback into the clock rate. So I'm going to take the sample and hold out. So this is our sample and held noise, and run it into CV1 here on the top half of Sport Modulator, which is working as our clock. And as you can hear, this is going to create a unsteady clock signal. This is going to make our gates much more free. So this is pretty similar to how a module like Wogglebug behaves on its gate output. So that's pretty much it for this patch. You could get more complicated with feedback, but this gets the job done pretty well, I think. Let's go ahead and move on to the next patch. Okay, for our next patch, I'm going to go ahead and get rid of this feedback routing. So now we're going to try to patch up a Bernoulli gate. I'm not for sure if I'm saying that correctly, but this patch will be essentially trying to recreate from scratch the module called Branches by Mutable Instruments. I realize that Branches has a few different modes, so we are maybe just recreating one of them. So as I said before, Branches takes an input. There's a probability control that controls the likelihood that the input will pass to one of two different outputs. So it's a natural extension of what we're doing here. So we are going to need two outputs. One that is high when the input, our sample and held noise, is in the window, and one that is high when it is not in the window. Now this specific compare to module by your analog has an out and a not out. If your comparator does not have a not output, you can use different logic modules for that, and there's a few ways to patch it up with other modules. So we discovered that we needed to use AND logic so that when our probability control was maximum, we would hear all the gate signals coming through, and we're going to need to do that again. But now we are going to need two AND logic functions. But that's not a big deal because AND logic is really easy to patch up. It's basically the same thing as a VCA. On a VCA, you have a main input and a CV input, and they both need to be high for us to hear something, or for a signal to pass. So I could use fails, channels 3 and 4, to create two AND logics. But I'm actually going to use select 2 because it's just close by, and it works really well for this purpose. So you might be wondering, why do I need to patch up two AND logic functions when I already have one? I've noticed that when I'm using the out and the not for this purpose, I get some behavior that's a little strange that I don't quite understand. I think it has something to do with how if the input signal, let's say, is in the window, and then on the next clock it's just not going to be in the window, it does take another clock to determine that, so it does pass temporarily. So we get all these moments where both outputs pass the gate, and using an external AND has solved that for me. This is part of the patch that I honestly don't quite follow, but I know that this works. So let's try it. The first thing we'll do is mult our clock signal and send it to the second input on both channels of select 2. The second input is only active when there's a gate on the select input. Then we'll send our normal output from our comparator to that select input on the top channel, and then the not output to the select input on the bottom channel. Now let's connect our select 2 outputs to our envelopes. And now our two logic blocks are complete. When the normal output on the comparator is high, our clock signal will pass to this contour 1. It'll trigger this contour 1, which is modulating the amplitude of our higher voice. When the not output is high on the comparator, it'll pass the clock to our second voice. It'll trigger our second voice, which is our lower generate 3. So to help us hear this, I'm going to pan our higher voice to the left a little bit and our lower voice to the right a little bit, and let's see if it's working. It sounds like it is. So size is still our probability control. So let's turn it fully clockwise, so we should only hear our higher voice getting triggered. We'll increase our clock rate a little bit. And now let's actually go fully counterclockwise. And now only our lower voice should be getting triggered, and it is. Now let's do somewhere in the middle. And I think we have it. I don't hear them ever firing at the same time. We're getting to control the likelihood that one output will be chosen over the other. we have essentially recreated one of the modes on branches. So we've completed our Bernoulli Gate patch. That was a lot of fun. We have our Bernoulli Gate working properly. We've essentially patched up from scratch the mutable instruments branches module, or at least one of the modes. So if you wanted to modulate the probability control, you could always plug a modulation source into the size parameter. And I'll try to build up a little patch that uses that as well. So here's a little patch that I made that sort of expands on the Bernoulli Gate patch that we made before. I'm now modulating the probability control with orbit 3, and I'm also modulating the clock with feedback, which kind of harkens back to the free random gates patch we did. And then I kind of created another voice using contour 1. Everything you hear is just this patch. There's nothing off screen. Let's just have a listen. I also have some performance controls over here. So that was just a fun patch, sort of expanding on some of the topics we discussed today and providing just one example of some of the possibilities. Thank you so much for watching. If you liked the video, please hit that like button and subscribe to my channel. It really helps. All right, until next time.